what we observed experimentally in the laboratory there, and you end up with the identical bounds there. Okay, so in this case, again, we have a total of 4 rooms there. The s orbital, px, py, and pz. Mix them together, you end up with 4 different orbitals, new orbitals there. Well, with different orientation there, identical energy, and then this takes the tetrahedral. Electron configuration there. So in conclusion, there we say any central atoms that has 4 valence electron pairs with the tetrahedral electron group geometry will form sp3 hybridization. Okay, so based on the electron pair geometry on the central atom, you can predict the hybridization pattern. So any central atom that has 4 valence electron pairs will form sp3 hybrid orbital. So examples: methane. We already used methane as an example. Nitrogen in ammonia, oxygen in water. The hybridization situation on nitrogen and oxygen are all sp3 hybridized. As long as you have 4 valence electron groups around the central atom, it's sp3 hybridization. Okay. Now, what happens with the with other situations? Well, let's just first focus on the sp3 there. Now, the term sp3, the number on P, sp3, means you take all the 3 available p orbitals and you use them in the newly hybridized orbital. So you take 1 s orbital, 3 p orbital, mix them together, you end up with 3 plus 1. A total of 4 orbitals there. 3 plus 1, we did not put the number 1 in there. Okay. So in conclusion there, we say the central atom in a molecule with the combination for total sigma bounds or lone pairs, as long as you have 4 valence electron pairs on the central atom, the hybridization at the central atom is sp3. Now remember, one of the objectives that we need you to be able to do is that you need to be able to predict the hybridization pattern on the central atom. So when you have 4 valence electron pairs on the central atom, it's sp3. Water, 4 valence electron pair. Anything that has a tetrahedral electron group geometry, you have an sp3 hybridization. Okay. Now, another example, boron trifluoride. We know this is one of the exceptions there. Boron has 3 valence electrons. These are the core electrons there. Okay. When you measure the boron-fluorine bound, these 2 electrons in the O theory are supposed, these 2 are identical, but this one is different. So we should end up with 2 different types of boron-fluorine bound, but that's not the case. When we measure the bound angle is all at 120 degrees. Okay, and what happens here is that with the 2 electrons on the s orbital, 1 electron on the p orbital, you have different electrons when they form the boron-fluorine bound. They're supposed to be different, but it's not. So Linus Pauling said, well, again, we need to modify the valence bound approach with the orbital hybridization. In this case, we have a total of 3 valence electrons. We have total of 4 rooms there, 2p and 2 px, py, pz with the 2s there. We need 3 new rooms. We need to reconstruct 3 new rooms there. So in this case, we take 2 of the 3 p orbitals available, mix it with the s orbital. We end up with a new set of sp2 hybrid orbital. The sp2, you take 2 of the p orbital, the remaining s there. You have a set of 3 orbitals there. Now, we put 1 electron in each of those hybrid orbitals. Now notice that there is a p orbital that's not hybridized, that's not being used. Now that p orbital is being used for forming the pi bound. Okay, so it's the hybridized orbitals are responsible for forming the sigma bound. The p orbital, the unhybridized p orbital, is used to form the pi bound there. So in this case, for boron trifluoride there, we end up with 3 identical electrons in the newly hybridized orbital there. As a result, when the fluorine comes in, they will be able to bound with each of the hybridized orbital. And since they have the same energy, you end up with the same identical boron-fluorine bound. So again, in this case, orbital hybridization theory goes that we have to do some reconstruction of the available orbitals that we have there, and we have to come up with a set of new orbitals with the same energy, one with each hybrid orbital with one electron in there. Okay, so as a result here, we end up with 3 orbitals there, and we end up with the sp2 hybridization. So in this case, any central atom, remember we're talking about the central atom, in the hybridization we're talking about the central atom there. Any central atom that has 3 valence electron pairs with a trigonoplanar electron group geometry will form sp2 hybrid orbital. Okay, so conclusion there is that when a central atom has a trigonoplanar electron pair geometry, it is most likely to bound through sp2. So we have sp3. This is one of the patterns there. Now we introduce sp2. Again, the number 3 and 2 indicates the number of p orbitals that we take in for mixing them up and reconstructing a set of new hybrid orbital. S, we took the s orbital. Electrons will occupy the lowest energy orbital available. So s orbital is always going to be the first orbital that we're going to use for the new construction. And then p orbital, depending on how many electrons we have there, we can take all 3 of them. We can take 2 of them. Okay? So in this case, we end up with a sp2 hybridization. Now there is one p orbital not hybridized in this particular situation. That unhybridized orbital is used to accommodate the pi bound. Okay? So whenever you see a double bound, there's an sp2 hybridization. That's a relationship there. Okay, and then for another molecule there, beryllium dichloride, for example. Beryllium, group 2A, you get 2 valence electrons. According to the old theory, those 2 electrons are squeezed into the same room because 2s orbital can accommodate up to 2 electrons. Well, the thing here is that we really don't need, for this particular example, we really don't need a new set of hybrid orbital there. But hey, you got 3 rooms not used. Why you cramp those 2 people in the same room there? Why don't you just take one of the 3 unused rooms there and forming a new set of hybrid orbital? Put 1 electron in each. And then in that case, you end up with what we call the sp hybridization. You take one of the 3 p orbitals, mix it with the s orbital, you end up with the sp hybridization. So in this case, the formation of the sp hybrid orbital are any central atom that has a linear electron group geometry can form sp hybrid orbitals. Okay, so you take one of the 3 and say which one, x, y, or anyone, because px, py, and pz, they have the same orbital, the same energy there. It doesn't really matter which one you use. And for example, for illustration purposes, well, let's take px orbital. We would have the py and pz unhybridized orbital still available for taking in other electrons, other types of electrons there. Okay, so in this case, when we have a triple bound, we would have 2 unhybridized p orbitals to accommodate those 2 pi bounds in there. And also in the situation where we have carbon, when you have adjacent double bound on the same central atom, you would also have sp